Thank you very much, Thug Crowd, for running this conference. Hopefully everyone's having a good time in this crazy new virtual world that we live in. This talk is about modern Linux heap exploitation. And basically, the idea is to give you the strategy on how to exploit a modern Linux system using the native heap allocator, which is in glibc ptmalloc2. And I'll divide it into three parts, this talk. I'll talk about heap allocator internals, specifically looking at ptmalloc2. I'll look at Linux exploitation in general, or how to gain code execution in a sort of a modern Linux system. And a modern Linux system, of course, in default user land does not include control flow integrity. So that's okay, we can hijack control flow. And then I'll talk about how to combine that with our heap allocator internals and how to gain code execution using ptmalloc2. So we'll start off with heap allocator internals. And, you know, very sort of introductory slide, what is virtual memory? Virtual memory is the thing that your user land process sees. And virtual memory is a linear or contiguous address space. It's a very uniform address space, which is much better than the underlying physical memory, which is non-contiguous and quite problematic. But that's what the kernel works with. But in user land, from a process point of view, all processes see memory effectively the same way, as a very contiguous, uniform look at memory. In a modern sort of operating system in a file format, we typically have executable code in our process image or our memory image. Sometimes this is called a text segment or text. We typically have a heap for dynamic memory management as well. And we have a stack for environment, the environment that's available. Things like environment variables go there and program arguments and so forth. We have local variables within procedures and procedure metadata, such as return addresses from procedures as well. Within that address space as well, and on a multi-threaded system, you might have multiple stacks as well. You also have shared libraries, and all of these shared libraries effectively have the same thing as well. They have the executable code. They might have their own code and data as well. But that's all copied into the address space, and due to the magic of sort of the underlying operating system kernel, it has its own view or its own copy, but it's only copied physically when that memory is modified or written to, so it's full copy on write. So this is sort of what your, a badly written program would look like. We've allocated 20 bytes using the heap allocator, which in Linux glibc is ptmalloc2. We've copied our first command line argument into that buffer, and then we freed that pointer. And of course, we have an unbounded string copy here as well, which could cause a heap overflow. And these are the types of bugs that we're looking at. Now, when we think about that buffer that got allocated in the last slide, it allocated, I suppose we'll call it a chunk. And malloc chunks are really the basic data structure in ptmalloc2, the default glibc Linux user land allocator. And malloc chunks either contain allocated or unallocated memory. So it can be both. If you free a chunk of memory, becomes unallocated memory. Now, surrounding this chunk is inline metadata. And this is one of the features, well, one of the things about ptmalloc2 is it surrounds application data with inline metadata that is potentially corruptible. Now, I talked about an in-use chunk or an allocated or an unallocated chunk of memory. So an in-use chunk of memory immediately preceding that chunk payload, which is the buffer that got allocated, is a size field. It also contains a few bits for flags, such as whether the previous chunk is in use, whether it came from an arena, and whether it's been nmapped as well. So that's sort of an in-use chunk. Now, a free chunk also contains that size field preceding the chunk payload, well, the original chunk payload. And then after, sort of at the end of the chunk, is also the size, so another copy of the size, which is sort of interesting. But more importantly for us, inside the old payload data, it's been repurposed just to maintain pointers, keeping them as part of linked lists. So this forward and back, and this forward next size and back next size are pointers that maintain these free chunks of memory in linked lists. And this is potentially corruptible if we have a use after free, where we can write to that chunk then we might be able to corrupt those linked lists. And this is sort of one of the main points of heap exploitation, I suppose, is we can corrupt these pointers and make them do interesting things. So these pointers maintain them on lists known as free lists. So when a chunk is freed, it's given back to the allocator, and the allocator, instead of putting it back into system memory, stores it as parts of these free lists so that a future allocation might be able to recycle these free chunks quite quickly. Okay, so that's sort of the basic strategy. There's a recycling strategy that a future allocation might recycle these free chunks of memory. And so when you free a chunk, it's sort of the first point of call is to try to put it into one of these free lists and give that malloc the chance to recycle them. Now, the Linux allocator follows a binning strategy, and bins are basically free lists as well. And the reason that they're called binning is that instead of sort of having one single free list, you have a bunch of free lists that each occupy a particular malloc chunk size range. And that's the binning approach, to take a very large number and to divide it into small ranges and associate each of these small ranges with a particular bin or a particular free list. So different chunk sizes go into different bins, and bins can also be thread specific. In fact, there's a per thread cache or a T-cache specific to the threads. So we'll look at a simplified bin. So this is sort of one of the main sort of things that we're going to look at attacking or corrupting. We'll look at a simplified bin. So we allocate some memory. Our bin currently is free. Doesn't have any items in it, sorry. We allocate some more memory. We still don't have anything in our bins. Remember, our bins recycle are placeholders so that we can later recycle free chunks. So when we free something, it goes into our bin. So we free chunk C, it went into our bin. We free another chunk, we free B. And this is one that we allocated earlier, and our chunk now gets inserted at the head of this free list. And we have two nodes now in our free list. So it's a last in, first out structure, or a stack. So we added something to the head of the stack. And now we're going to free a third chunk. And again, that goes to our head of our list. So we've got three chunks in our bin, simplified bin, but this is really how our bins work in the real world. When we go to allocate something, we've allocated 10 bytes of memory again, but we allocate something like we've allocated before. And in fact, we're going to recycle our chunk from our free list. And we popped off A and gave it back to the userland application requesting it. We request another 10 bytes of memory, and we've recycled this chunk again. We've popped it off the head on the top of that free list, and we've done it as well. We still have one item in our free list. We're going to free another chunk now, and again, it goes back to the top of the free list, or the head of the free list, very much like a stack. And that's basically what a free list is. That's basically how most of the free lists work. In general, free lists are last in, first out structures, or LIFO structures, or in sort of common language, they'd be called a stack. So there's actually a number of bins that ptmalloc uses. You have you have unsorted, small, large bins, and so forth. Fast bins. These are all different types of bins for different types of functionalities. Fast bins here are shown as singly linked lists, and then we have small and large bins, and the unsorted bins, which are different types of bins. They're doubly linked lists. So those are sort of the main sort of data structures when we work with free lists, and they're singly linked lists and doubly linked lists. Another concept that we have to understand is an arena. An arena stores basically heaps, entire heaps as an arena structure. And the reason that there are multiple arenas in an application is it's basically to reduce thread contention. If you had all allocations from all your threads going into a single arena, they'd all be contending for that global heap locking structures or synchronization primitives. So you have separate heaps to separate arenas, and it reduces thread contention. So where is the metadata? What can we modify if we have a heap corruption? So PT-Malloc2 uses metadata before and after each allocated buffer, as well as using before and after and inside unallocated buffers. So what types of things can we corrupt from a heap overflow? So the size information we could certainly corrupt. And you're thinking, what can you do by corrupting the size field? Well, when you free a chunk of memory, the way that it knows the size of the chunk and therefore the associated bin holding these free chunks is the size field, the metadata before the payload. So if you modify the size field and free a chunk thinking that it's much larger, it'll go into the wrong size bin. And then when a future allocation occurs, it'll reclaim that incorrect size, and maybe that chunk now will overlap adjacent data. So you might have overlapping chunks here. Also, those free list pointers, and I'll talk about this later on, but those free list pointers, if you corrupt a free list pointer, you could make malloc return an arbitrary pointer. You could make malloc return that arbitrary pointer that you corrupted this free list singly linked list with. Now, also, what types of things can you reveal from a memory disclosure? So pointers in free lists, in these free lists, remember those, the payload of an unallocated chunk. Pointers in those can point to global heap structures in standard C libraries or libc. And so you might be able to reveal the libc base address and defeat ASLR. And you also might get pointers to dynamic heap data structures as well. Okay, so we'll go on to, we've looked at heap allocator internals now. Let's talk about exploitation. So pretty much when you're an attacker, what do you do with the bug? You've got a bug, what's the purpose? Generally, sort of the modern approach is to try to gain some sort of primitives that leverage that bug into arbitrary code execution. And the types of primitives that you're after, you want the ability to write to what you want anywhere in memory, sort of a write what where primitive, maybe a restricted ability to write to memory, the ability to read memory, an arbitrary read write primitive, the disclosure of the memory layout. These are the types of primitives that enable you to gain code execution. So let's assume that an attacker has a read write primitive. This is we'll assume that an attacker has reached this point where they've leveraged the bug and they've gained a read write primitive. How do they turn that into code execution on a current Linux user land application? You need two things. You need an information link. So you need to be able to read, from memory to gain an information link that discloses the address of libc in memory, the standard C library memory, that shared library in the address space. And the reason you want to disclose the libc base address or the ASLR layer is that you want to hijack control flow and overwrite an existing function pointer, such as in libc, and overwrite that with the code, point that to the code that you want to execute, and then have the application call this function pointer. So this is what you need for sort of modern Linux exploitation. You want an info link to disclose the libc base address, and then that will let you know where in libc to overwrite a known function pointer to point to the code that you want to execute, and you've hijacked control flow. There is no control flow integrity in userland default at the moment, so this is an entirely valid approach. Now, where do you get function pointers from? Now, this is the part of research, I suppose. We know the strategy. We just want to override a function pointer, point it to a beginning of our rock chain or a stack pivot or something like that. Maybe point it to a one gadget to get a shell really quickly. So, what function pointers are available that we can overwrite to hijack control flow on a modern Linux system? So, historically, the global offset table was a good place to find function pointers. And the global offset table is basically a list of writable function pointers present in almost all executables. All dynamically linked executables have a global offset tables, and these contain pointers to library functions such that when you call printf, it'll look up the global offset table via the procedural linkage table, and the global offset table will hold the resolved address of that printf in our shared library in the address space. And so classic heap exploitation would overwrite the GOT entry with the pointer to your shell code. You know, the application calls the library call associated with the GOT entry, maybe printf, maybe malloc, something like that, and the attackers now hijack control flow. So that's sort of historical. So the GOT as a source of function pointers no longer works on most systems. There's a mitigation, in fact, called read-only relocations that resolves all the library symbols at program load time and remaps the GOT as readable but not writable. So you can't hijack this at runtime because it's not writable anymore. And even though I say that this no longer works on most systems today, there are applications out there that have writable GOTs, such as Firefox. You can do this attack on Firefox today. But this is really what we consider historical. Firefox will fix this, I'm sure, at some point in the future. So, you know, how do you exploit, modern applications that have this reasonable mitigation that is pretty much present in every executable? So, you know, can you do it? Yes, modern control flow hijacking is still very possible if you know where libc is loaded in memory, because there are standard function pointers at fixed offsets in libc. So the modern standard C library has a number of known function pointers as offsets from their libc base address. So the at-exit handlers are one example of function pointers. This is a little bit harder because there's a mitigation known as pointer guard that obfuscates those function pointers. But two things that aren't obfuscated and you can overwrite directly are the runtime linker locking functions. This is part of sort of the runtime linker. And probably the most well-known and common one are malloc hooks. For every malloc and calloc and realloc call, there's a function pointer associated with it that is for application-specific malloc API. So if you want to have your own custom malloc, you would overwrite the malloc hook with your function pointer that you want, and then you are able to hijack when malloc is called. You're able to do that. Now you can actually defeat ASLR as well. So you need to know the libc base to do that malloc hook hijacking, and we'll be able to do that later on. But if you don't want to defeat, the libc base address, there are other techniques as well. Now, if the binary is not compiled position independent, and modern binaries are, but certainly some out there don't compile in position independent, then the PLT and the GOT that I just talked about, that global offset table, is at a fixed address when the program loads. So libc will still use ASLR, but the PLT and the GOT is at a fixed address. So how can you get the libc base address given that the PLT and the GOT is a fixed address? Now, if you're able to hijack control flow from some sort of Stack Overflow or something like that, then you can actually return control flow into the right system call, which is in the GOT and the PLT. And what you're going to write to standard output are the contents of a GOT entry for a resolved library call. And this will actually print the address that it is in libc for this particular call. And that's at a fixed offset from the libc base. And now you can actually know the base address of libc, even though the libc was at a random address, but the PLT and the GOT wasn't. So the basic idea is that if you have a non-randomized PLT or GOT, then you can disclose the libc base address. Now, this attack is mostly historical now. The modern mitigation is to use a position-independent executable, and this will remap the PLT and the GOT at randomized addresses on every execution. You can't return into the PLT unless you get the address first of that randomized text and data segment. Now, if you're on 32-bit, and many CTF style challenges are 32-bit still, some are, not all of them. The entropy on a 32-bit system is actually very small. So it's actually very easy to defeat ASLR on a 32-bit system. You simply have to run your exploit 1,000 times without changing any of your fixed addresses for one run. And by statistics, you'll brute force it almost certainly and completely defeat ASLR. And you'll probably get it, somewhere between 100 and 1,000 iterations, you'll defeat ASLR on 32 bits because the entropy is so small. Now, if you have multiple libraries that you're trying to brute force, and they're all loaded independently with ASLR, then it takes much longer to defeat. So you have the time of one library multiplied by the time of the second library and so forth. So you want to try to keep your exploits only using one library, ideally. And then it's quite fast to defeat. You don't always need to defeat ASLR for an exploit to work. What you can take advantage of as well is that what you've got to remember is libc is just a small contiguous region of memory. So if you have a function pointer in to somewhere in libc, such as printf or so forth, and you want to modify that function pointer to point somewhere else in libc, maybe to malloc or a one gadget that executes a shell, you don't need to modify the entire 8 bytes, 8-byte pointer. You simply have to modify the low bytes of the pointer. And then you can bypass ASLR altogether. You can redirect an existing libc function pointer to another libc function pointer by only modifying 1 or 2 bytes. Your exploit might not be 100% reliable, but this is a pretty reasonable technique if you want to redirect or change one function pointer to another function pointer. Now, is it possible to write reliable exploits with ASLR on a 64-bit Linux that uses position-independent executables and all other mitigations? Absolutely. You need an information disclosure on the Linux heap to disclose a pointer as part of those free lists which point to fixed structures in libc and that disclose the libc base address. So all you need to do is have the ability to read a bit of memory off the heap, have the heap laid out in a certain way that gives you a pointer that's useful, and you've got the libc base address. So the final part of the talk is looking at Linux heap exploitation. Now, so historical heap exploitation on Linux was based around dlmalloc. That was the precursor to ptmalloc. The attack is effectively you overflow a heap allocated buffer and you overwrite those linked list pointers that we talked about earlier. And when effectively a node is unlinked from a linked list, such as removing it from a free list, that pointer manipulation through that unlinking process gives the attacker the ability to write what they want and where they want in memory via those pointer operations. And this is known as the unlink attack. It was developed by Solver Designer against Netscape Navigator. And there's a lot of history about this. He was the first guy to develop the first non-executable stack patch on Linux. He developed, in the same post that he talked about non-executable stacks, he developed Return to libc, which is the precursor to ROP, and he now develops the open wall Linux distribution. So he did this in the year 2000. This was really the birthplace of heap exploitation, the first generic heap exploitation. Unlink has been dead for about 15 years, hasn't worked for a long time. You don't really see this too commonly today. Some embedded allocators, this attack still works on. So some embedded libc and IoT devices, this attack still works. But effectively, unlink has been modified, mitigated by checking that the linked list pointers look reasonable. So if you start at a node and you go forward and backwards, you end up at the same place in this linked list. So from about 2005, there's been an era of post-unlink heap exploitation. And this has carried on through to today. There's been about 15 years of research of exploitation. And there are many, many techniques that work today. There's probably a dozen, 2 dozen techniques on Linux glibc that work to attack the Linux heap. Now, modern heap metadata exploitation, you're unlikely to get a write, what, where primitive. Instead, what the goal should be, well, you can do other things besides a write, what, where. You can make malloc return an arbitrary pointer decided by the attacker. You could have it a near arbitrary pointer. You can make malloc return an already allocated heap buffer, or you might make malloc return a buffer that overlaps another heap allocated buffer. So these are the types of attacks you can do on not only ptmalloc2, but a bunch of allocators as well. Now, if you make malloc return an arbitrary pointer and an attacker can write to that what would be a legitimate buffer normally, maybe it's user input, attacker input, or something like that. If an attacker can do that, and that's application logic now, then control flow hijacking is very likely. So what you want to do is you want to make malloc return an arbitrary pointer and make it point to a function pointer. For example, the GOT or a malloc hook that's in libc. We know the base address of libc because we did that information disclosure. And if the attacker, writes to that buffer and they simply substitute the beginning of their rock chain, or they could substitute the pointer to the one gadget, then they can hijack control flow. Now, sort of that's the attack. That's really how modern exploitation works in this context. You make malloc return an arbitrary pointer, you override a function pointer, you know the libc base address, so you know where to write that function pointer to, and you know where to get a one gadget or a rock chain and so forth, and you can hijack control flow. Now, you typically need to lay out the heap, so your heap corruptions corrupt the right chunks, and generally need some level of interactivity with your application, to lay out memory, to get info leaks and so forth. And it might not always be 100% reliable. But other than that, control flow hijacking is certainly possible on a current system with all mitigations, providing the application is reasonably suitable for this type of exploit. And remember, how do we get malloc to return an arbitrary pointer? We talked about getting malloc to return an arbitrary pointer. Those free lists, we simply have to corrupt a pointer in those free lists to point to our arbitrary address. That's really all we have to do. That's all we have to do with the heap corruption, and malloc will subsequently return our arbitrary address, and with appropriate application logic, we can leverage that into our ability to write what we want wherever we want in memory. Now, Linux mitigations are generally not state-of-the-art mitigations compared to, say, software on an iPhone. Control flow hijacking, which I talked about here, has been central to exploitation for decades. Control flow integrity, pointer authentication, and other techniques are forcing exploitation techniques to continue and do things like data-only attacks, which is really where we are now. And this, of course, raises the cost of attackers to succeed in memory corruption exploitation. Now, the cat and mouse game of attack and defend has been active pretty much for my entire career. But, over that career, we've certainly continued to have exploits. Mitigations do raise the bar, but exploitation is still very possible. Now, heap exploitation is still an active area of research on all operating systems, and all heap allocators still have weaknesses. So thank you very much for listening, and I hope everyone gained something from that. And I'll go over to questions now, but my headphones have just ran out of charge, so I might have to take them on the chat perhaps.
Well, thank you, Silvio. We got you. That was awesome. Again, like I mentioned before, Silvio does do a lot of this stuff in his trainings as well. Also, B-Sides Canberra this weekend was supposed to be this weekend, and Silvio has come and joined us here to do this talk.